In this video, we focus on comparing groups. We will learn how to conduct and interpret hypothesis tests of two variances, and how to conduct and fully interpret a one-way analysis of variance, often called one-way ANOVA. You will practice the full homework process for each method, deciding when to use it, naming the variables, writing null and alternative hypotheses, checking conditions, entering the right information into software, locating the correct values in the output, and writing conclusions in complete sentences. Before we start, it helps to separate two kinds of group comparison questions. Sometimes the question is about averages, meaning group means. Sometimes the question is about consistency, meaning spread. Averages are about where the data center. Spread is about how tightly the data cluster, or how widely they vary. Variability describes how spread out data values are. Two groups can have the same average but very different spread. Imagine two classes both have an average exam score of 75. In one class, most scores are between 70 and 80. In the other class, scores range from 50 to 100. The averages match, but the second class is far less consistent. A variance measures that spread numerically. A standard deviation is another common measure of spread. Variance is the standard deviation squared. A hypothesis test of two variances is used when your question is about spread rather than average. You use this test when you have two independent groups and you want to know whether one population is more variable than the other, or whether the variability differs at all. The hypotheses for a two-variance test must be written about population variances. The null hypothesis states that the population variances are equal. The alternative hypothesis depends on the question. If you are checking for any difference, the alternative states that the variances are not equal. If you are checking whether one group is more variable, the alternative states that variance 1 is greater than variance 2. If you are checking whether one group is less variable, the alternative states that variance 1 is less than variance 2. A two-variance test uses an F-statistic. The F-statistic is calculated by dividing one sample variance by the other sample variance. Because variances are always positive, the F-statistic is always positive. It helps to interpret the F-statistic in everyday language. The F-statistic is a spread comparison ratio. If the spreads are similar, the ratio will be close to 1. If the numerator group is much more spread out than the denominator group, the ratio will be noticeably larger than 1. The F distribution tells us how unusual a ratio that large would be if the population variances were truly equal. Before performing a two-variance test, check conditions. The samples must be independent. Each population should be approximately normally distributed. Variance tests are sensitive to non-normal data, especially strong skewness and extreme outliers, so this condition matters more here than it does in many mean tests. To run a two-variance test in software, the program will typically ask you for the two groups of data. Many homework sets give raw data values in two columns. In that case, you select the two data sets. Some homework sets give summary statistics. In that case, the program may ask for sample size and either variance or standard deviation for each group, depending on the option you choose. If your homework gives standard deviations but the software expects variances, remember that variance is standard deviation squared. You would square the standard deviation to get a variance. If the software allows raw data entry, you can avoid this step because the software will compute the sample variance automatically from the data. After you enter the data, the software will ask for the alternative hypothesis direction and the significance level. Then it will output an F-statistic and a p-value. Now we interpret the p-value for the two-variance test. The p-value represents the probability of observing a ratio of sample variances at least as extreme as the one calculated, assuming the population variances are equal. It measures how surprising the observed spread difference would be if the null hypothesis were true. A small p-value means the observed variance ratio would be unlikely if the population variances were equal. That supports rejecting the null hypothesis. A large p-value means a variance ratio like this is reasonably plausible under the null hypothesis, so the data do not provide strong evidence of different population variances. Example 1 for a two-variance test. Suppose we compare completion time variability for two training programs, Program A and Program B. The null hypothesis states that the population variance of completion times is the same for both programs. The alternative hypothesis states that the population variances are not equal. In the software, we select the two groups of completion times or enter their summaries, choose a two-sided alternative, and choose a significance level such as 0.05. Suppose the output reports an F statistic of 2.4 and a p-value of 0.01. Because 0.01 is less than 0.05, we reject the null hypothesis. We conclude that there is sufficient evidence that the population variances of completion time differ between Program A and Program B. Interpreted in words, the data suggest the two programs do not have the same level of consistency in completion times. Example 2 for a two-variance test showing fail to reject. Suppose we run a similar comparison, and the output reports a p-value of 0.30. Because 0.30 is greater than 0.05, we fail to reject the null hypothesis. We conclude that there is insufficient evidence that the population variances differ. Interpreted in words, the observed difference in spread could reasonably be explained by random sampling variation. Now we shift to one-way ANOVA. One-way ANOVA is used when your question is about averages across three or more independent groups. This is the group comparison tool you use when there is one categorical grouping variable with three or more categories, and one quantitative response variable. A one-way ANOVA answers this question. Do at least two population means differ, or are the differences among sample means small enough to be consistent with random sampling variation? This is a single overall test for all groups at once. The null hypothesis for one-way ANOVA states that all population means are equal across the groups. The alternative hypothesis states that at least one population mean differs. The alternative does not tell us which mean is different. It only states that not all means are equal. One-way ANOVA works by comparing two sources of variation. Between group variation measures how far the group means are from the overall mean. Within group variation measures how much individual observations vary around their own group mean. The ANOVA F statistic is the ratio of between group variation to within group variation. If group means are very similar, the between group variation will be small relative to within group variation, and F will be close to 1. If group means differ more than expected by chance, the between group variation will be large relative to within group variation, and F will be larger. Before performing one-way ANOVA, check conditions. The groups must be independent. The response variable should be approximately normally distributed within each group, especially when sample sizes are small. The group variances should be approximately equal, which is often described as similar spreads across groups. Software may show group standard deviations to help you judge whether spreads look reasonably similar. To run one-way ANOVA in software, you need to know how your data are arranged. Sometimes the data are stacked, meaning all response values are in one column and a second column labels the group for each value. Sometimes the data are unstacked, meaning each group has its own column of response values. Software typically supports either format. The key idea is that you must provide the quantitative response and the categorical group labels in a way the program recognizes. The software output usually includes an ANOVA table. The table commonly includes rows labeled between groups and within groups. It also includes degrees of freedom, sum of squares, mean squares, the F statistic, and the p-value. You are not required to compute these by hand for this course. You are expected to interpret the F statistic and p-value correctly, and explain what the result means about the population means. To interpret an ANOVA table, you can use a consistent reading routine. First, locate the between groups row. Second, find the F statistic and the p-value associated with the overall test. Third, compare the p-value to your significance level. Fourth, make the reject or fail to reject decision. Fifth, Write the conclusion in context about the population means. Now we interpret the p-value in ANOVA. The p-value represents the probability of observing differences among the sample means at least as large as the observed differences, assuming that all population means are equal. It measures how surprising the pattern of group mean differences would be if the null hypothesis were true. A small p-value in ANOVA means that differences among the sample means this large would be unlikely if all population means were truly equal. That supports rejecting the null hypothesis. A large p-value means that differences like these are reasonably plausible under the null hypothesis, so the data do not provide strong evidence that population means differ. Example 1 for ANOVA. Suppose we compare exam scores across 3 teaching methods: Method A, Method B, and Method C. The grouping variable is teaching method, which has 3 categories. The response variable is exam score, which is quantitative. Suppose the sample means are 70, 78, and 82. We write the hypotheses. The null hypothesis states that the population mean exam scores are equal for methods A, B, and C. The alternative hypothesis states that at least one of the population mean exam scores differs. We enter the response data and group labels into the software, choose a significance level such as 0.05, and run one-way ANOVA. Suppose the ANOVA table reports an F statistic of 6.1 and a p-value of 0.003. Because 0.003 is less than 0.05, we reject the null hypothesis. We conclude that there is sufficient evidence that not all population mean exam scores are equal across the 3 teaching methods. A small p-value here means that the observed differences among the sample means are unlikely to be explained by random sampling variation alone if the population means were truly equal. Example 2 for ANOVA showing fail to reject. Suppose we compare average wait times across 4 service centers. The grouping variable is service center with 4 categories. The response variable is wait time in minutes. Suppose the software reports an F statistic of 1.2 and a p-value of 0.32. Because 0.32 is greater than 0.05, we fail to reject the null hypothesis. We conclude that there is insufficient evidence to suggest that the population mean wait times differ across the 4 service centers. A larger p-value means the differences among sample means are not unusual under the assumption of equal population means. ANOVA tells us whether at least one mean differs, but it does not tell us which groups differ. If we reject the null hypothesis, the next step is post hoc analysis, also called multiple comparisons. The software may produce pairwise comparisons between groups with adjusted p-values. The adjustment is important because when we compare many pairs, the chance of a false positive increases unless we control for it. A key rule for homework is that post hoc comparisons are interpreted after a significant overall ANOVA result. If the overall ANOVA p-value is not significant, you usually stop and do not interpret post hoc differences, because the overall test did not provide strong evidence that the means differ. Post hoc example continuing the teaching method scenario. Suppose the post hoc output shows an adjusted p-value of 0.01 for method A versus method C, an adjusted p-value of 0.20 for method A versus method B, and an adjusted p-value of 0.14 for method B versus method C. We interpret that output by comparing each adjusted p-value to the significance level. The A versus C comparison has a p-value smaller than 0.05. So we conclude that the population mean exam scores differ between method A and method C. The other comparisons have p-values larger than 0.05, so we conclude there is insufficient evidence of differences between A and between B and C. A complete written conclusion after post hoc tests should keep the focus on population means and include group names. A strong conclusion might say that there is evidence of a difference in mean exam scores between method A and method C, while differences involving method B were not statistically significant at the chosen significance level. To complete homework problems for these topics, follow a consistent structure. First, decide whether the question is about spread or about averages. If it is spread and there are two independent groups, set up a two-variance test. If it is averages and there are three or more groups, set up one-way ANOVA. Second, identify the variables and groups. Third, write the null and alternative hypotheses in terms of population variances or population means. Fourth, choose the significance level. Fifth, enter the correct data or summary information into software. Sixth, locate the p-value and compare it to the significance level. Seventh, write the decision and conclusion in context. For ANOVA, if you reject, interpret the post hoc comparisons to identify which groups differ.